Good afternoon, everyone. Thank you for being here. My name is Korhan Sevinç, and I study computer science at Top University and uh, working in Roketsan currently in Ankara. Today, I'm going to talk about my work, LatentGLoss. It's a new way to train a text classifier for mental health texts. First of all, let me start with the why. Mental health is a big topic today. The WHO, aka the World Health Organization, and the European Union both say the same thing. We must find problems early. And here is the interesting part. People already show their feelings in text, in posts, in chats, in forums. This happens every day, also between doctor visits. But this text is difficult because it's short, it's informal. Uh, People do not write explicitly just like I'm depressed. They say it in an indirect way. You can probably tell that they're depressed, but you need to acknowledge their situation first. So we need models that understand this kind of text. And also one more thing, the model must be cheap to run because we want to use them all the time, and also we want to be able to accomplish this task with less GPU, VRAM, and quicker. So that was the goal, reach the quality of a big transformer model, but at a much lower cost. Our contribution is the training methodology. We call it dual latent GNet. It is a teacher-student method with a new loss. We call it latent G. The idea is simple to say, that the student does not only copy the teacher's answers, it also learns the teacher's inner features. It learns how to regularize itself like teacher, so it is not copying the teacher's answers, but it learns the distribution that the teacher answers coming from. For the experiments, we joined 9 public datasets into one benchmark, and I will show you it on the next slide. And the result is our method beats a fine-tuned BERT model, but at the test time, it is only a small CNN. A few words about the data I want to say. We combine 9 public datasets. Just like I said, the text come from posts, tweets, and short chats. Every text gets one of the 7 labels, as you can see on the right. Anxiety, normal; depression, suicidal; stress, bipolar, or personality disorder. All texts go through the same pipeline. First, we do the pre-processing, we clean the text. Then we use back translation for data augmentation, which is basically we translate the text from English to French and back to English. So we preserve the same semantic meaning, but we use it with different words for that particular sentence. So we got a richer data set, and this gives us more training examples and a good data augmentation. So this is the data set that we are working on with, and this was the pre-processing steps. Now it is time for the key idea. You probably know the knowledge distillation. A big teacher model trains a small student model. Normally, the student copies the teacher's output scores, so the student learns what the teacher outputs or predicts. Our idea is that is not enough, and we also want to know where the predictions live inside the teacher's feature space. We want that our student model learns how to regularize itself like teacher, so it is not copying the teacher's answers, but it learns the distribution that the teacher's answers. This is the key idea that I'm trying to emphasize. So if you could just look at the diagram on the right, the teacher is a CNN, a convolutional neural network with 2 training goals. We take its inner features and its output scores. Then we fit a Gaussian mixture model, a GMM, on this feature space. So now every class is like a cluster. And in the empirical studies that we have done, we generally think that it is the best practice that selecting the same number of Gaussian mixture models num class parameter as the number of dataset classes. When we train the student also makes a feature vector. We find the best cluster for it, and we pull the student towards that cluster. So the student learns from two signals, the answer and the geometry of the feature space. The second signal is the latent G term in our name. To accomplish this, we deduce a new loss function, and we use cross entropy plus this information that I'm talking about as a classification loss, and mean square error as the reconstruction loss. Here is the full architecture. On the left, you can see the CNN backbone. It reads the text and creates a latent vector, the inner features. This vector goes to two different heads, two different decoders. The first one is the classification decoder, and it predicts the class. This was our goal. And the second one is the reconstruction decoder. It tries to rebuild the input. We have two goals because together they create a rich and useful feature space, a rich latent features. So classification alone is not enough. And with reconstruction, the features keep more information about the text. This model is our teacher and our student architecture. So we use this because its feature space is good enough to teach the students. Now here's the how we train part. There are three simple steps actually. The first two steps are not the actual students training, but we need a teacher model and its latent features plus the prediction logics, and we need to fit a Gaussian mixture model to them, so we can get the clusters. So let me start with the step one. At the step one, we train the teacher convolutional neural network, the architecture that I've shown in the previous slide, with its two goals: classify the text and rebuild the text. Both losses shape the feature space. And at the step two, after the teacher is ready, we take its features and its output scores, put them together, we concatenate them into a single vector, and fit the GMM, fit the Gaussian mixture model on them. We do this only once before the student training. At the step three, we train the student for every text. The student makes its own vector for every text. We find the best Gaussian mixture model cluster for it, and we measure the distance to the teacher's feature. These two values, the cluster probability and the distance, form our loss function, LatentGLoss. And one more detail about the loss function. This loss becomes stronger during training. At the start, the student learns the basic tasks, and later we pull it more and more towards the teacher's geometry. And by that I mean, by epochs, we are increasing the weight of the latent G component. So while the latent G component's weight is increasing, the reconstruction and all the other things' weights are decreasing. And if you need more detailed information on this, you can check the original paper. Now I'm going to talk about the experiments. Our experiments are simple and fair. We have one data set, the same train and test splits for every model, the same text cleaning, and the same data augmentation. So the differences come from the models, not from the data. And we compare four groups: classical TF-IDF models, which are classical machine learning algorithms and models like SVM and random forests. We compare CNN, RNN models, fine-tuned transformer models like BERT, Distelbert, Albert, and Roberta, and our dual latent GNet architecture. We measure accuracy, precision, recall, and advanced scores. And here are the results. The chart shows the best model of each group. The best classical model, random forest, reaches about 93%. The best RNN model, LSTM, reaches 94.1%. And our own teacher, the dual CNN, reaches 93%. 95%. The strongest transformer, fine-tuned BERT, reaches 94.83%. And as the orange bar, as you can see, our dual latent GNet architecture reaches 95.09%. It is the best of all groups. It is higher than BERT, just a little, and it is about 2 points higher than its own teacher. So the improvement comes from our training method, not from the CNN itself. The difference to BERT is small, but it's stable, and we can see it on accuracy, precision, recall, and advanced scores. And I want to talk about why this is important. Well, first, the scientific point. The teacher's inner features hold information, and sometimes the transformer miss that information. When the student matches these features, it gains accuracy on top of the answers. And second, later, the practical point. At test time, only the small student runs. There is no transformer, so you get transformer level accuracy at CNN cost. This is useful when you want to run the model often or on a small hardware. For the future work, we want to put a pre-trained encoder inside the student or the teacher and keep the latent G part. So we combine strong language features with our geometric training. And secondly, we want the model to show its uncertainty, not only a single answer, and we want to make it even smaller for devices with low resources. To conclude, LatentGLoss teaches a small model the inner features of a big one, and on mental health text, it reaches 95% above a fine-tuned BERT at low CNN cost. The code, the data, and the model files are on GitHub. You can see the link here. If you have any more questions, you can always contact me from this email. Thank you very much for your attention. I hope you will be having a nice day. Thank you.